So let's go for German Shepherd and upload there. So drag and drop. I'm dragging and dropping here. So let's see. This is the breed recognition. Wow, it returned German Shepherd. Let's go for this Siberian Husky and let's drag and drop. Let's see what it will return. Wow, it returned Siberian Husky. Let's go for Golden Retriever. Wow, 3 times the model predicted correctly. Let's go for this Beagle breed. Drop here. This time our model failed because the accuracy is 62%. Let's go for this Poodle. Yes, it is returning standard Poodle. Let's go for the Chihuahua. Yeah, it is returning Chihuahua. Hello friends, welcome back for another deep learning image classification project using efficient nets. The main purpose of this project is about using the efficient nets, transfer learning with efficient nets, and fine tuning of efficient nets. So for this I am using Stanford dogs dataset, and for accelerating my training I am using the accelerator TPU, and I am also using the latest environment. Here you can see I have added the Stanford dogs dataset as dataset in the input section. Then this is the output directory. Then accelerator is TPU, language is Python, and persistence is variables and files. So if TPU get disconnected, the variables and files that we saved will be saved and we can use after restarting the kernel again. So let's start. At first I'm importing libraries like NumPy for numerical calculations, TensorFlow and Keras for building the model, and Matplotlib for visualizing the data. Then I have also imported EfficientNet B0 from applications module of Keras. Then imported JobLib for saving the breeds of dogs. So let's run this cell. Yes. Then as I am using TPU accelerator, for that I have to create the TPU strategy. So whenever you are creating a TPU strategy, make sure that you have these 4 lines of code and which is mentioned in the official document. That first you have to create a resolver, and if you are using Google Colab, you don't need to mention this TPU equal to local, but if you are using Kaggle notebook or any other notebook, you have to mention the local so that the local TPU machine will be connected. Then to create a TPU strategy, we have TPU strategy method in the distribute module of TensorFlow library, and there we have to pass the resolver and it will return as strategy. So let's see the number of replicas in the strategy. For that you can apply the attribute num replicas in sync to the strategy variable, and it will return the number of cores. So let's run this. Yes, our TPU is initializing. Yeah, we have 8 cores, you can see, and then I'm creating some parameters which will be used later, like image size, batch size, and auto tune. So here for this specific case, as we are using efficient net B0, so for it we have to have the images of size 224, 224, 3 channels. For that reason I am using 224 as image size, and this is mentioned in the paper where efficient nets are discussed. So make sure that your image size is 224 when you are using efficient net B0. After that I am creating batch size. So as we have 8 number of cores, so for each core I am allocating 64 examples. That's why 64 times of 8, that is my batch size. And for auto tuning the number of parallel calls or buffer sizes which will be used later, I am using the tf.data.autotune. That means TensorFlow will automatically detect the number of parallel processing units, and which is saved in autotune variable. So let's run this and create these parameters. It is taking some time. Then I'm creating the datasets, train DS and test DS. So in Keras we have a method which creates image dataset directly from directory, that is available in utils module of Keras. The name of the method is image dataset from directory. Here we have to pass some arguments like path of the directory, subset, that is whether to return both train DS and test DS, or only training or only validation. And then validation split is 0.2, that means 20% of data will be reserved for validation purpose, that is here in this case test DS. Then batch size, so that batches will be formed, and image size, so that images will be resized to this size, and shuffle equal to true, that means the dataset will be shuffled, and seed equal to 1331. It is for reproducing if we want to recreate the dataset. So this is the file path, and if you want to know the file path you can go here. Then in datasets we have Stanford docs dataset, click over here. Then we have 2 subdirectory inside this main directory, then click over images. So under the images we have these subdirectories for different breeds. So I am going with this directory path and pasted over here, and from there I am creating the datasets. So let's run and create our train DS as well as test DS. So for that press shift enter. So yes, here you can see it found 20,580 files belonging to 120 classes, and from 20,580 files, 16,464 files are reserved for training and 4,116 files reserved for validation. After that, let's go for class names and number of classes. As already it has shown 120 classes, we will save this. So let's run this. So to get the class names, we have attribute class underscore names, which should be applied either to train DS or validation DS or test DS, which will return us the class names. And I am showing only first 5 class names and also the number of classes. Let's run it. So here you can see these are the 5 class names, and we have 120 classes. Then I am creating labels out of class names, as the class names are a mix of some numbers and characters. So I just want to get the characters out of the whole numbers and characters. For that, I am iterating over class names, and in each class name I am splitting over the days, and from there I am taking out the first part and saving that in the variable label and appending in the labels empty list. After that, I am showing the first 5 breeds, and labels are nothing but the breeds. So add another line, that is job leave dot dump labels as labels dot job leave. This means that we are saving the labels using the job leave with the method dump. This is the file name that we are going to create. So let's run this. So you can see first 5 labels are this, and the labels are successfully saved in the file name labels.joblib. Then let's see the shape of image batch and label batch. So you can see we have 512 examples in a batch with image height 224, image width 224, and 3 channels, and 512 labels in each batch of labels. After that, I am showing the 9 images from a random batch. For that, I am going with a for loop and taking out one batch from trained DS and then splitting it into image batch and label batch, and iterating over first 9 images of image batch and first 9 labels of label batch, and showing them using IamShow method of matplotlib. So let's run this and see the first 9 images. You can see this is a Pekingese breed dog, This is Dandy Dinmouth breed dog. This is Selkie Terrier breed dog, and these are different breeds of dog. After that, I have augmentation layers. In augmentation, I am having random rotation, random translation, random flip, and random contrast layers, and for that I am defining a method to augment each image to these layers, and after augmentation the defined function will return the image. So let's run it. Yes, the augmentation layers and augmenter is created. Then I am pre-processing the images, and here using the map method, mapping the augmenter to image and level with the lambda method, and using the argument number of parallel calls equal to auto tune in the map method, so that the number of pre-processing cores required by the TensorFlow will be detected by the TensorFlow itself, then prefetching with auto tune, so that the dataset required in the second epoch will be fetched in the first epoch, or dataset required in the nth epoch will be fetched in the n-1th epoch. Let's run it. So train DS and test DS are augmented as well as prefetched. Then let's build and compile a efficient net B0 from scratch. So to build from scratch, we have the class name efficient net B0, and inside that we have to pass some arguments like include top, widths, classes, and input step. So as we are building it from scratch, so we are including top equal to true, that means the top layer will be included, but when we go for transfer learning we will mention include top equal to false. Then we are initializing no weights to this efficient net B0 because we are going to train it from scratch. Then we have to pass the number of classes in the classes argument, and as already I have told that efficient net B0 requires the image size of 224, 224 with 3 channels. So that is the input step, and this is saved in a variable model under the strategy scope. Then compiling the model with Adam optimizer, sparse categorical cross entropy, and matrix as accuracy. You may be confused about that I am using sparse categorical cross entropy because already the levels are in the format integers and I have not pre-processed it into one hot encoded. So I am not going with only categorical cross entropy, rather I am using sparse categorical cross entropy because levels are in the format integers. So let's build the model and compile the model. So some warning it has returned at first, and under the strategy.scope we have to build the model and compile the model so as to use the accelerator. Then let's train the model with 40 epochs. So one thing I want to say that whenever you are training the model, it should be with a minimum of 10 epochs and maximum of 100 epochs. Using the fit method applied to the model, I am training it with train ds and specified the validation data as test ds. So let's run it and train the model. So at first we will get some warnings. Don't worry about warnings, these are common when we use TPU accelerators. So as we are training the efficient nets from scratch, it will give poor accuracy on validation data. So don't worry, we will improve it using the transfer learning, and here you can see the next step is transfer learning. So we are training the model from scratch, and as I already told that the purpose of this video is to use the efficient nets in transfer learning, but I am training the model from scratch. It's just to show the difference between accuracy when we train the model from scratch and use the model with pre-trained weights. Don't worry about the time, I will increase the speed when it trains. After 39 epochs, you can see the training accuracy is 42%, loss is 2.0357, validation accuracy is 0.2815, that is 28%, and validation loss is 3.1891. So after 40 epoch, the training accuracy reached to 0.4519, that is equal to 45%. Loss is 2.0092. Validation accuracy is 0.2570, that is 25%, and validation loss is 3.0669. So if we train the model from scratch, the maximum training accuracy is 45% and the maximum validation accuracy is 28%. So if we use the efficient net with pre-trained weights, then we can get a good accuracy if we will remove the top layer and go for a new top layer in the efficient net. So let's build the model again and let's do the transfer learning with pre-trained ImageNet weights of efficient net B0. So for that, let the input is this, that is with image size comma 3, and using the efficient net b0 method we are removing the top layer, that is the classification dense layer. So to remove it, mention the argument include top equal to false, then passing the input tensor to the efficient net, that is this inputs, and we are retaining the weights of ImageNet pre-trained already, and then we are setting the model trainable equal to false, so that the feature extraction layers remain its weights freezed. And here we are adding the top layer with a block. At first we have a global average pooling layer which takes the input of this model's output. Then we have a batch normalization layer, then a dropout layer, and at last we have a dense layer with 120 number of classes and softmax activation function. Then we are rebuilding the model with the model method of Keras, specifying the required inputs and outputs. So this is what we do in transfer learning. So at first you have to load the pre-trained model without the top classification layer. Then you need to freeze the base model, which prevents the updates in the feature extractors. Then add the custom classification layer, then train on new dataset. This is what the first step we have to do in transfer learning. So let's run it. Then under the strategy scope, build the model, and whenever you are doing transfer learning, make sure that the learning rate is a greater value or higher value. So here we are using 0.01. The 1 e means nothing but 0.01. So use higher learning rate when you are doing the first step, that is transfer learning. And here we are going with the same optimizer Adam and same loss, sparse categorical cross entropy, and same metric accuracy. So let's build and compile the model under the scope. Yes, you see here the weights are downloaded, and then the next step is to train. To train the model, I am using fit method, and inside that I have specified some arguments like dataset is trained yes, number of epochs is 25, and the range of epochs is 8 to 80 when you are doing transfer learning with efficient nets. Then specified validation data as tested yes and a callback early stopping. So early stopping will monitor our validation accuracy, and it has presence of 10 epochs, so it will monitor for 10th epochs. If the validation accuracy does not improve, then it will stop training. Then and the last argument in the callback is restore best weights. So the maximum validation accuracy epochs weights will be restored in the model. So let's run it and train our model with 25 epochs. You will see some change in the validation accuracy. You notice here the maximum validation accuracy is 28% and the last validation accuracy is 25%. But when we do transfer learning, you see the improvement of validation accuracy over here. So let's wait. Training is done only to the classification layer that we just added in the model, and all the feature extractor layers will remain freezed. So it is returning some warnings, don't worry. So yes, first step is completed. Here you can see the accuracy is 0.3 for training case and validation accuracy is 0.54. Wow, what a change, great change. 54% validation accuracy is obtained, and here you can see we had 28% only, the maximum, while we trained it from scratch. But when we did transfer learning, it retained and resulted. Now after second epoch we got 58% validation in accuracy. Wow, it is increasing. Superb. After 24 epochs, we reached to a training accuracy of 0.7441, that means 74%, and loss equal to 0.8385. Validation accuracy is equal to 0.6213, that is 62%. A great increment in validation accuracy. Where is 22% and where is 64% now after 25 epochs? So that is the use case of transfer learning. After transfer learning, we will fine tune the model. So fine tuning means nothing but unfreezing the freezed feature extractor layers in the base model, which will improve the adaptation to the dataset. And you should remember that base normalization layer need to be kept frozen when you do fine tuning, and never open up all the layers to unfreeze, only open up a portion of layers to unfreeze. And also do not use RMS prop when you do fine tuning. Use a smaller learning rate, and smaller batch is effective when working with fine tuning. So these are the steps that I followed. So you can see under the strategy scope, I am unfreezing the top 20 layers only. Then if the layer is not a batch normalization layer, then I am setting the layer to trainable. Then using the optimizer atom with a very small learning rate, that is equals to 1 e minus 5, there is nothing but 0.00001, and compiling it with the same optimizer, same loss and same metric. So let's execute this cell. So yes, now we are opening up last or top 20 layers. Then let's train the top 20 layers for adapting with dataset. So to train, I am again using the train ds and test ds for validation, and here you should mention 4 to 10 epochs only for training, and also I am using a callback early stopping with these arguments, that is nothing but monitoring validation accuracy with patience number of epochs equal to 2 and restoring the best weights. So let's train it. If the extractor layers is worked well with a pre-trained dataset, then there won't be much difference or much increment in the validation accuracy, as we are using efficient net. So it is already trained with good amount of docs, and our feature extracting layers are well trained enough. That's why we won't see much difference in the validation after fine tuning. I hope so. Let's see. So after first epoch, the training accuracy is 0.7325, that is 73%, and training loss is 0.91692. And let's wait for validation accuracy and validation loss. So you can see the validation accuracy is 0.6198 and validation loss is 1.3992. It's because already our feature extracting layers are well trained with a huge dataset with good number of docs, so we won't get much improvement, but this is the general strategy followed when transfer learning with a pre-trained model. After fourth epoch, you can see the validation accuracy is 67% and training accuracy is 76%. So let's evaluate the model, and it will return a dictionary. Then I am saving the model. That's the last step. Yes, the accuracy is 62% and loss is 1.45, and let's save the model. After saving the model, you can get the model to download in this output section. So here you can see labels.joblib that we already saved, then model.keras, then this is a db. So click over the three dots to download, then you will get a download button. So thank you for watching. Thanks a lot. Hello friends, let's build an interface for Stanford dogs classification to classify the dogs into their breeds or recognize the breed. So at first I'm importing libraries like Streamlit for building the interface, TensorFlow and Keras for reloading the model and doing the TensorFlow operations, PIL read the image uploaded by the user, NumPy for numerical calculation, joblib to load the labels. So using load model method, I'm loading this model in the file path model.keras. Then using the load method of joblib, I'm loading the labels inside the labels.joblib file path. Then I'm creating a container for title which contains two columns, one for image, another for heading, with the different width sizes, and the vertical alignment argument equal to center in columns. If we go with this argument center, then the contents inside these columns will start from the center. Under the image column, I have a image of width 150 in this location. The image is located, and under the heading column we have two write methods. One is a title dog breed recognition, another is a description about the dog breed recognition. That is, dog breed recognition is a deep learning neural network model built using efficient net for recognizing the breed of a dog that the user wants to know. After that, I have a container for input and output. So inside the container we have a file uploader where user can upload a dog image, and we have the argument accept multiple files equal to false. That means user can upload one file at a time. Then if the image is uploaded, then I am creating two columns with equal width sizes and named them as input call, output call without any borders, and the vertical alignment is center. That means the content inside these columns starts from the center. Under the input column we have a heading like info section showing input image, and then showing the image uploaded by the user with the width size of the column. So I have used here use container width equal to true. That means it will occupy the width of whole column. Then under the output column we have a success heading with the title breed recognition. Then using the image module and its method open, we are reading the image and saving that in the image variable. Then as our efficient net model needs resolution of 224, 224, so I am resizing the image with and saving that in the same variable, then expanding the dimensions so as to get the base size. After that, using that image to predict, and this is applied to the model, and if we get the prediction, we are getting the index of the maximum value of the prediction, because the prediction will return 120 values as a array, and it will contain different values for different indexes, and the maximum value will be the output. For that I am getting the index and applying that index, fetching the label name, then showing that with rainbow color, and the first character is capitalized. That's why I am using the title to the string that we get from these labels, and showing the output using write method. Then we have another container for sharing the contents. Under this container we have 3 columns with equal width sizes and without any borders. The names of the columns are YouTube call, LinkedIn call, Hugging Face call. So inside each column we have a link button. So under the YouTube call I am giving the YouTube video output, and under the LinkedIn call I am giving the URL to LinkedIn. Inside the Hugging Face column I am giving the URL for space of the project. To run this file, open up the terminal. So to open terminal in the VS Code editor, press Ctrl tilde. So check your directory where this file is located, and to run this file enter streamlit run app.py, then press enter. So you will be redirected to the application. So already I have searched about dog breeds. So when we get the application, we will check whether our app is working properly or not. So we have got 62% of accuracy when we created the model. So do not expect much accuracy. So let's go for this, and let me make it 2 parts. So let's go for German Shepherd and upload there. So drag and drop. I'm dragging and dropping here. So let's see, this is the breed recognition. Wow, it returned German Shepherd. Let's go for this Siberian Husky and let's drag and drop. Let's see what it will return. Wow, it returned Siberian Husky. Let's go for Golden Retriever. Wow, 3 times the model predicted correctly. Let's go for this Beagle breed. Drop here. This time our model failed because the accuracy is 62%. Let's go for this Poodle. Yes, it is returning standard Poodle. Let's go for the Chihuahua. Yeah, it is returning Chihuahua. Thank you.